Well, first let me thank Monica as well as Angela and Miles for invitation and effort for organizing such a successful online series of PD seminar for our community. It's my pleasure and honor to be invited for the talk today, in particular after such an inspiring talk by Professor John Ball 10 minutes ago. In this talk, I would like to discuss some underlying connections between nonlinear PD of mixed elliptic and hyperbolic type, and some fundamental problems in fluid mechanics, differential geometry, and the related area, and discuss some recent development in solving these mixed type problems through the connections. Well, let me start with some background. Well, it's well known, of course, two of basic type of linear partial differential equations, elliptic type and hyperbolic type. The typical representative for hyperbolic equations is a wave equation, which describes wave propagations. And for elliptic equation is the Laplace equation, describes the equilibrium state. Right? So solutions called some harmonic function or potential functions. So those equation looks very similar. Right? Also, you could regard the solution of Laplace equation is the steady state of the wave equations. But the solution behaviors of those two solutions are very different. So since that, the Adama proposed the classification for second order partial differential equation. So this classification very successful for two-dimensional constant coefficient second order PDEs. For constant coefficient second order PD, now coefficient Aij, you can write 2x2 matrices. So this symmetric matrix have two real eigenvalues. If both eigenvalues the same sign, this is the elliptic, otherwise the hyperbolic. Now, if the same sign, you through coordinate transformation, you can transform general this second order PD to the Laplace equation, otherwise to be wave equation. So this classification, of course, similar to the classification for like algebra curves, conic section, and the quadratic form in algebra geometry. This also can be seen through Fourier transform. If you take a Fourier transform both sides, then you got coefficient quadratic form for Fourier frequency, for then the multiplied Fourier transform unknown function. So if you divide this quadratic part to the right hand side, for elliptic case, you purely gain two order decay for high frequency Fourier in the high frequency in Fourier modes. So you get the two regularity. For hyperbolic, of course, you cannot get fully purely two order because it's general. This is for constant coefficient case. Now for variable coefficients, the problem are more delicate. Since in this case, coefficients depend location x, y. Now the same, we have 2x2 matrices, then we got two real eigenvalues. But very often, the two eigenvalues change sign in different regions. So I now give the three examples. This is show you this kind of typical examples of the fundamental equations now we know for that. The first example for the sine functions, in the coefficient jump. So when x less than 0, this is the wave equation. Then x bigger than those Laplace equation, but transition slow jump after x equals 0. Now, Jacobi equation and the Keldysh equation slow transition continuously. They exhibit different kinds of degeneracy. Okay, one is hyperbolic degeneracy, the other is parabolic degeneracy. So for linear case, although this mixed type, but we know the transition boundary because determined by x, y. Right. So we know region which part hyperbolic, which part elliptic. So one of the approach to handle such kind of problem, of course, you will first study elliptic region up to transonic boundary, a transition boundary with degenerate elliptic problem. Then other side, the hyperbolic side, you call degenerate hyperbolic problem. Then if we understand the solution for degenerate hyperbolic, degenerate elliptic, then we more or less understand the behavior of solution near the transition boundary. Another approach, of course, the fundamental solution. If you find the fundamental solution globally, understand the behavior of fundamental solution near transition boundary. So more or less you understand the behavior of solution near the transition boundary. Okay. So this is for linear case. So today I want to give you several examples to show you actually many nonlinear partial differential equations arising from fluid mechanics, differential geometry, and related areas. They are not a single type. Actually, even more often, they are mixed type and no type even. Okay. So, on the other hand, the solution of those fundamental problems require a deeper understanding of nonlinear partial differential equation of mixed elliptic and hyperbolic type, which needs a really new idea, mathematical idea, techniques, and approach deserve our attention for that. So first example, I want to very old problem actually in fluid dynamics called steady shock problem. Steady transonic flow onto solid wedge when wedge angle less than critical angle we call detachment angle. For this problem, actually there are two solutions very simply. Each solution involves a shock wave and two constant states. Shock wave roughly speaking mathematically means a co-dimensional surface. A closed surface solution like density, physical quantity for density velocity have jumped for satisfy of entropy conditions. So for these two solutions, the first solution called strong shock means the subsonic behind that always subsonic, means elliptic hyperbolic to elliptic through the shock wave. The other solution is dependent angle called sonic angle. If angle less than sonic angle, hyperbolic subsonic to subsonic to state. If angle bigger than sonic, it becomes subsonic, also subsonic. So here even constant state, but this involves a mixed elliptic hyperbolic problem here. So this problem now, then we have a non-uniqueness issue here. The question whether both solutions are physically admissible. And if yes, what kind of mathematical reasoning, underlying mathematical reasoning? If not, we exclude one of them. This caught attention first by Planck. He, based on the experimental result, he conjectured one of solution called weak shock solution is physical admissible. He also proposed dynamic configuration such that T goes to infinity, this solution, dynamic configuration, asymptotically approach this weak shock solution. So in some way, like if we can verify it, that means we can verify weak shock is a physical and the time step asymptotically stable. So this problem then when Coulomb-Friedrich then in 1940s, when they wrote this book, they systematically analyze this problem and document all analytic results before experimental results before that. Here, eventually they got the following conclusion. It indicated that I quote here. It has frequently been stated that the strong one is unstable, and therefore only weak one could occur. And a conventional proof of this instability has apparently never been given. So this got caught attention by von Neumann. He organized a panel discussion in Paris in 1949 during the joint conference by International Union of Theoretical Applied Mechanics and the International Astronomical Union. And he invited several prominent scientists of that day, including Burgers, Hessenberg, Lippmann, von Karman. The topic is really exactly about this non-uniqueness issue. Okay, so he started the panel discussion, really point out some of which are very difficult to be excluded on mathematical grounds only for non-uniqueness issue. Then he put this example, I'll just show you. And then he pointed out, in general, there are two different solutions with short waves. It's perfectly well known from experimentation that only one of two weak short waves occur in nature. He pointed out, well, I think all stability argument to prove that it must be so of very dubious quality. So he was not very optimistic. See how to clarify this issue. Only mathematical grounds only. Okay. So about 20 years ago, we started this project, and then we searched extensively all literature. We thought after that, to see what kind of result we got. To our surprise, then actually we could not find a really significant progress in terms of mathematical argument for this problem. So how to handle this problem? Well, first step, of course, we think about the steady case, and we do in the steady framework, everything's steady, and we perturb incoming flow, we perturb wedge boundary. See whether both solutions, like weak and strong shock, are both statically stable. So this is the first question. It turns out for hyperbolic cases, the weak shock hyperbolic cases, the supersonic supersonic, they are resolved earlier. There are various like Gui-Qiang and many others. So listening through this last 50 years, we clarified of all various research together, and we conclusion is that for static case, both solutions are statically stable. Of course, in a little different sense, but we convinced that is true. Okay, so we could not exclude the solution in the steady framework. So next question, of course, what about dynamically? Can we really construct dynamic solution? And our dynamic solution asymptotically goes to one of them or both. So this come out of the Planto configurations. From experimental result and the numerical simulation show that when supersonic flow come in, then you create a shock here from here. Then this shock depend angle. If angle less than sonic angle, first part shock straight line, behind follow with the shock of straight line. Only problem between them, there's a very solution of very complex structure here. Okay, so this is the question now, whether such kind of conflict we can prove it from our PDE and set up a problem, initial boundary value problem, and whether we could do it. Okay, so the Planto conjecture think this is stable for weak shock. So we start that is the case. So now for some of you may say, well, this problem so concrete, so simple. Why so many scientists and mathematicians care that? One of the reasons, of course, the non-uniqueness issue. Another underlying reason is that those configuration actually is one of typical configuration in the Riemann solution of Riemann problem, two-dimensional Riemann for hyperbolic conservation law. So then we have PDE first order, second order. Initial data, now Riemann problem means your initial data is a special initial data, such that initial only depend angle. Therefore, those kinds of initial data, we can easily find initial data such that the solution experiment numerically, we can see that those solutions contain the configuration I just showed you, like Planto-Mayer configurations. On the other hand, the Riemann solution we know play very important role in the theorem, mathematical theorem of hyperbolic conservation law. This Riemann solution determines asymptotic state and global attractor. Also determine local structure and as the building blocks of general entropy solutions. So if we want to understand the solution structure or behavior of general entropy solutions for two-dimensional hyperbolic hyperbolic conservation law, we have to understand those kind of configurations. So let me now first focus on Euler equation for potential flow. PDE are chosen is this system. The first equation is the conservation mass. The second equation, Bernoulli law. I like this system because the first equation, if we know density, loss density, gamma constant. If we know density, then this second equation really Hamilton-Jacobi equation. Now, if we know velocity potential, then the first equation transport equation. So this is a system coupling each other between the transport type equation and the Hamilton-Jacobi type equation. Now, from second equation, if we represent the density in terms of phi, then plug in first equation, then we got nonlinear wave equation. So this is actually one of early motivation why we study nonlinear wave equation. It turns out in history, this equation is one of the earliest PDE and was written down with that. So this is our PDE we're focusing on. Okay, so what is our problem? Problem really initial boundary value problem. Initially, we have incoming flow, then wedge is solid wedge, so it's slip boundary conditions. So whole problem is now we have PDE, we have initial condition, boundary conditions. Those configurations suppose a solution of this initial boundary value problem. Now you look at this problem carefully. Actually, this problem is invariant on the self-similar scaling. Means you Px you invent this way, scaling, and the low phi in this scaling. So for any alpha, the initial data is invariant, but slip boundary conditions is invariant, and the PDE are invariant. The system or one equation that is invariant. So naturally, we're looking for self-similar solution. This also motivated the numerical simulation. The solution looks like self-similar. So now the self-similar variable, then we get the new quadratic sign this form. Now for convenient, shift the quadratic part, term phi, now phi we call pseudo potential. This is phi potential. Reason you shift the quadratic form, then a lot of equation phi is a quasi-linear second order PDE, coefficient independent sign eta. So this is looks very nice, and then the reason why I introduced quadratic form outside for that. Now this PDE second order looks very neat, but this is really mixed elliptic hyperbolic type. Second, this equation that elliptic if grading phi has this relation and otherwise hyperbolic. So this is one example very naturally from physics. We come out in very nature second order nonlinear PDE of mixed elliptic hyperbolic type. Now, of course, before you solve problem, you even don't know which region is this equation elliptic, which region hyperbolic, until you solve the problem and you get a grading estimate related with solution. Then you know, oh, here's the elliptic region, there hyperbolic. So this is very different from a linear case. Those kind of models also there are many simpler models, and early in the literature on fluid dynamics, I just list here. They are a little simpler than this model I early derived, but they are mixed elliptic hyperbolic. For PDE like this one, then what up initial boundary value problem? Initial boundary value problem then become boundary value problem in unbounded domain. Slip boundary can still keep the same, but initial condition become asymptotic boundary condition. When t goes to 0, cosine eta goes to infinity. Okay, so the solution configuration supposes is a solution of this boundary value problem in unbounded domain for mixed elliptic nonlinear PDE, second order PDE of mixed elliptic hyperbolic type. Now, so look careful analysis. If we're looking for solution bounded, gradient phi bounded, then outside that from infinity, actually is always hyperbolic. So we can use hyperbolic theorem to reduce the whole problem. Actually, outside we can make sure prove the nonlinear wave equation always constant. Then we can determine too short. location. This is like a normal reflex shock. This is what I choose weak shock. I showed you earlier, like standard weak shock at this point, right? Then you can solve nonlinear wave equation, this region and this region, as you prove that this is mass constant and unique. So whole part, we can really determine all this region, and we don't know this part solution from outside to inside, whether inside the elliptic, outside the hyperbolic, the shock with this form. If this is the case, then this problem involves two kinds of transonic flow. One is from hyperbolic to elliptic through degenerate curve here. Other part is from hyperbolic to elliptic through the shock wave. They jumped, rebounded. So now I talk about shock wave several times. Now, mathematically, how to define shock wave in case you haven't heard about that. Shock wave means that I mentioned earlier, the co-dimensional one surface, which connected by two regions. Okay. Suppose we know solution, smooth solution, both region, but separated by the co-dimension surface or curve. Now here's a curve with two-dimensional cosine eta plane. Then can you put the two solutions together, satisfy equation in the sense of distribution? Answer is no. You need the necessarily sufficient condition about the trace of solution along the curve from left side and the right side. So this is physicist called Lincoln-Hoogle condition. For mathematicians, this is just a basic requirement of we try to get a global solution such that the satisfy equation in the sense of distribution. So this is normal, in this case, the two conditions, algebra conditions. Then of course, the satisfy entropy condition determined by signal thermodynamics, which in this case, the density increase across the shock in pursuit of flow direction. So the such kind of curve we call shock. Now with that, problem we can reduce boundary problem for mixed type of PD. I've started with a small angle. And we regard the shock as free boundary. Then the shock, we have two conditions, Lincoln-Hoogle conditions. And we hope we prove inside of the elliptic, okay, subsonic. Now, if subsonic, the same reason I mentioned earlier. Now, if we find a solution here, we want to put it together. Although this degenerate curve is not shock wave, but this is weak discontinuity. So in order to solution put together satisfy equation, two sides, in the sense of distribution, you need not only phi match, you also derivative should match. So you need those conditions to satisfy not only one condition. Of course, if this elliptic is a strict elliptic, then we cannot give so many conditions on fixed boundary, right? So only hope, because our elliptic equation, if we put inside the elliptic degenerate along the curve, so not only match delicious condition, also non-match condition. So this, of course, we have to resolve it before you really complete the proof. Otherwise, overdetermined. Okay. So who issues does such a solution, the Platin-Mayer configuration, exist globally in general? One case I point out when wedge angle less than sonic angle. Another case of course wedge angle between sonic or detachment angle. Then what type of optimal regularities about this solution? Okay. So I put there's some early result by Elliptic for first case. They get a certain regime. They could answer construct a solution like that. Okay. So the question further, we are really still general case whether possible. So the several difficulty here, of course, one I already mentioned, the nonlinear PD of mixed elliptic hyperbolic type. And other hand, the free boundary. Free boundary now we have to touch to this elliptic. If this inside the elliptic, we have to touch to the degenerate curve, connect the free boundary to fixed point. And this problem cannot formulate the evaluation of form. So we have to find a new approach to handle such free boundary problem. Another thing, of course, I mentioned the two conditions, the non-match condition, the liquid to match. So we need the optimal estimate for degenerate elliptic PDE here. This is very important. Another corner was fully bounded with formed by degenerate curve at this corner. What the optimal regularity? As well as this shock with if this detect before solid, because they saw it with a wedge angle here. In this case, because PDE without the growth condition, there are many results about non-elliptic with growth condition handle cornerless singularity. In our case, we don't have growth condition actually even. So there are other questions like geometric properties of free boundary. So here's the theorem. We can prove that. Answer is yes. For wedge angle less than sonic angle, we really can prove this such conflict exists globally. And the shock actually match those 2 points with other shock, not only curvature, not only slope, curvature, even C2 alpha. And inside we can prove inside the elliptic. And transition from elliptic to hyperbolic not only match deletion in Neumann, even C11, okay, but C11 is optimal. And we also get a solution in the corner of the C11, the optimal regularities, and also various properties. So this is for angle less than sonic angle. Now when we increase angle, then reach to sonic angle, then this region becomes smaller and smaller, eventually reduced to 1 point. Means the general elliptic becomes 1 point at the corner. Then when angle bigger, a little bigger, then switch to purely elliptic. So this we could prove that the transition through the sonic angle, then between sonic angle, then we can prove similar those result hold. The same hold correspondingly, and the same thing now we got C11 here, and also this corner is the best optimal solution C11. This solution through here C2 alpha and the C1 alpha for that. Now the approach and the related techniques to prove this theory has been developed based on the ideal techniques from our early related work in this research monograph published 1 year ago by Princeton University Press. That we solve the different type of problems, shock and reflection different problems, and so this really give a motivation and also provide idea how to handle the problem here. One idea, of course, trying to see the iteration. Since free boundary, we introduce iteration procedures. Before that, we do all carefully a priori estimate. First, we want to prove some monotonicity property. For example, a cone formed by this slope or z slope in the direction inside the cone, phi is monotone, some kind of phi linear function has monotone property. Then we first make sure this free boundary is Lipschitz. Okay, that's the first step. Then also because angle we change from small angle through sonic angle to detachment angle, we need to first make sure C01 estimate, because we want to make sure inside ellipticity, keep ellipticity all the time. So this is very important, making sure this domain is bounded and not go infinitive, and always ellipticity inside away from the sonic circle, always uniform elliptic, independent of angle. Then very careful estimate, C2 alpha estimate in the domain, weighted estimate. Of course, we want to keep the C11 corners. So very careful to estimate. And this is quite technical to these 4 steps. Now, based on this a priori estimate, then we design the iteration set and the iteration map, such that they satisfy the 3 properties. This has to be checked carefully. And then we check the degree at the beginning. Then eventually we can use the Rayleigh short degree theorem, start from small angle to detachable angle. So this is just some ideas to handle that. I don't have time to explain that. Now, this is for, of course, weak shock, the Plateau-Meilleur configuration. The way to the strong Plateau-Meilleur configurations. So because strong at this point will be immediately from hyperbolic to elliptic, then picture like the previous picture where angle bigger than sonic angle. It turns out this can be excluded. This is impossible. This is basically the elliptic theorem. Because shock, you can formulate the oblique boundary condition. This is a deletion normal boundary condition. This is a corner. It turns out the coefficient vector of oblique condition for weak shock, strong shock, the different. So weak shock, we have flexibility. We give after this corner, we can give two conditions. For strong shock, we only can give one condition. So eventually, this can be proved the contradiction with the maximum principle. So it's impossible. And now then we've listened, we motivated by early work like free boundary problem for study geometric properties. The study like Kefler, other linear cases like Kefler, and many others, or even listen like Plantinnikov and John Turing about the proof convexity of water waves for that. So we also motivated by that, we also study whether those transonic shocks convex. Okay. So we've proved that, eventually found a way to prove that those transonic actually uniform convex, except of the ending points. Okay, away from ending point, always uniform convex. This really helps us now to prove uniqueness, the stability of global shock configuration, those kind of problems. This is still preprint. We will post archive maybe soon for that. So this is also applied to other problems. I just put here for that. So this is the one class of the example. I show you the physical problem, also looks very classical, but fundamental, but they are really related to the nonlinear PDE of mixed elliptic type. Now, second example, I want to show you from differential geometry is about asymmetric embedding problem. Well, we know that to give a curve, okay, surface, then you can compute the first fundamental form, you can compute second fundamental form and the curvature. The problem is opposite. Given metric or some property of curvature, can we construct a surface? Right. So this is seems a very basic question and very simple to be stated. But turns out this problem not so easy, quite complicated. So the problem play very essential role in the development of differential geometry and differential topology. And there are a lot of applications about understand the sophisticated shapes of surfaces or thin sheets in nature, in the elasticity, material science, and biology, even now the data science. And there are many mathematicians, especially differential geometry and geometric analysts working on this problem. They solve various cases. For generic setup of this problem, the whole problem is still open for that. Okay. So one result I want to mention the Nash's result. Nash shows that you give an n-dimensional Riemann manifold. This can be embedded into the Euclid space in the very biggest dimension. Okay, target dimension very high. So mathematically, really, we want to expect the solution optimal dimensions. It's called Janit dimension, which is n plus 1 divided 2. Okay? So the Nash shows that if the target dimension high enough, you have flexibility. So you can prove such asymmetric embedding if CK exists. Okay? So of course, for many applications, we really care optimal dimension. So the question is what are the lowest target dimension or rigidity of asymmetric embedding? Also regularity and what is optimal again? What is sign regularity? Find the regularity. This regularity also quite sensitive. If he give example in 1966, he proves that for two-dimensional method to asymmetric embedded to R3, actually no C2 asymmetric embeddings. So it's quite delicate for that. So what does the PDE now involve? So PDE involves really the fundamental theorem of the differential geometry. This for 3-dimension case, 2-dimension to 3-dimension. 2-dimension manifold to 3-dimension. Now, if you're given first fundamental form, now second fundamental form satisfy Kodaza equation and satisfy Gauss equation, then you can construct the surface, okay, in Euclid in R3. In the, of course, traditional geometry test was sufficient smooth, but this theorem actually true as long as second fundamental form in LP, P bigger than dimension. Now this is the Kodaza equation, really first order PDE, right? The 3 unknowns, now through Cauchy-Gauss equation. If we represent one of them into other 2 plugins here, first, then the first 2x2 system, okay, the first order system, which is the system of mixed elliptic and hyperbolic type. The type really depends the sign of Gauss curvature. Okay. So this kind of mixed type, the feature can observe. Of course, the Gauss curvature change the very nature like a so simple surface, right? You change the sign. One side. So, from PD point of view, this really mixed elliptic and hyperbolic. So this why this can be seen also through the fluid dynamic formalism. I took it from the paper with the Marshall Slammer, the one in CMP 2010. We found this formalism. Okay, if we error angle, we can write down this form, and with constitutive relation, we choose Chaplin type gas. The relation density velocity with this relation. Then Kodaza equation could become momentum equation, Balanced law of momentum equation. Gauss equation become Bernoulli relation basically for that. So this is really a system of the like fluid dynamic system. Previous example, I show you the one equation conservation mass, second equation Bernoulli law. Here now, example matches the balanced law of momentum equation and the Bernoulli law. Then mixed type, the type of change of type could see through like the similar like fluid dynamics, supersonic, and sonic dependent Gauss curvature corresponding there. So based on this observation, we formulated a framework for existence and weak continuity for Gauss-Kodaza equation, the weak converging method, special compensated compactness method, and I'll show you an idea now together with this is low dimension together with high dimension, especially for one of idea for that. So this is a 2-dimension to 3. Now, what about high dimension? If a dimension to Rn, then we should add the Lich equation. So system becomes Gauss-Kodaza Lich equation. So normally this system very big, dependent dimension, a huge system, and this system has no type basically. You cannot talk elliptic-hyperbolic even. In generic, really no type, very general system, very big system. On the other hand, nonlinearity, you look at the nonlinearity, this is all quadratic. Okay, here. So the question, can we, for example, weak rigidity? For example, we have sequence solution of the system, LP bounded. Can we prove the weak limit still solution of this problem equation, the system? So you have to pass the limit to those quadratic terms. Here's the answer, yes, this can be done, okay, for LP bigger than 2. Observation that this system has really beautiful, difficult structure. Okay. Left-hand side, this we call all formula the difficult. Right side are those RGS involve quadratic forms. Actually, basically 3 quadratic forms here. So now, if we know those solution LP, those quantity with LP divide 2, bigger than L1, then this is compact H minus 1, right? So this compact H minus, we can use difficult lemma, difficult structure. Left-hand side gives the quadratic form weakly continuous, path limit here. Then this weakly continuous quadratic form exactly those quadratic form involving right-hand side. So this is really beautiful, like God-given. From left-hand side, you have quadratic form, use some boundaries. From left-hand side, give the compact weakly continuity. But weakly continuous quantity exactly those quadratic form we want to pass limit. So some of you may be not familiar with difficult lemma. Okay, I just did have this classical difficult lemma could state the following. This is a beautiful lemma. We have two sequences LP and LQ, which is uniform bounded LP, LQ. Of course, this uniform bound, of course, difficult to uniform bound in W minus 1P. Well, if we ask a little more, instead of boundedness, we replace by compact subset. Okay, compact. Then we get a really beautiful statement. Inner product of the two vector field, the weakly limit weakly continuous. Okay, so no, generically we have ULP, LQ, this L1 uniform bounded. Then, of course, we know that L1 by uniform bounded, what is the weak limit? Well, in generically, even not the L1 function could be measured. But if you require a little bit more, then not only weak limit still L1, but weakly continuous. Now there are various extensions about this lemma for difficult lemma. Now we are concerned, now previously I showed you the local coordinate. Can we do globally, right, for manifold? So we extend this lemma now to the Banach space. We set up this lemma in the following. Main ideas are difficult to operate, differential operate. So we can generalize that general operate with adjoint operate. If this operator with other operator, adjoint operator, orthogonal, then they span the whole space. Basically, we can prove if this weak convergence in this Banach space, then you can do that. This is path limit in the Banach difficult lemma basically on a Banach space. Now this thing becomes a Banach space, then we can, as corollary, we can get intrinsic difficult lemma on remaining manifold independent of coordinate. So listen to we even extend the no abelian type one. So one result is that if seeking fundamental form or connection form bound uniform in P, you can generalize original local version to global version. Okay, then no matter of the equation we don't know type, we can do that manifold. More recently, we even now we don't need all both bounded. Recently, we prove that we only need the seeking fundamental LP bound. You give me a sequence of solution. If seeking fundamental bounded, then we can find a refined sequence. They are still weak solution, but limit is still solution goes to 5. So you don't need the normal bounded part, the connection form. Other part bounded, but only need the seeking fundamental bounded, you still can get those kind of weak continuity. So this we have to use the invariance or choice of suitable gauge to control full connection form. Okay, so this is well, I'll show you now. This is global weak regularity for Gauss-Quadrat equation way for Riemann manifold. Recently, we also extended to semi-Riemann manifold. Means the first fundamental form metric you don't have positive definite like a Lorentzian manifold. This also you can do it. We develop a uniform intrinsic geometry approach of the independent local coordinate. This also applied to now correspondingly the immersed surface as well. Of course, those class problem were motivated actually from the theorem of polyconvexity in nonlinear elasticity by John Ball. He started as a determinant then into the theorem of the polytron convexity. This also connects with the convex integration and the flexibility by Delele, listen to Delele, Sikhides, and many others after Gromov. Also connected with the Olympic compactness. And this idea we found also useful. We handle Yang-Mills equation and general immersion problems. So I'll just show you those basically two classes of examples. There are many other examples in applications involving nonlinear PDE or mixed elliptic-hyperbolic type. Well, some of them you could see from this book, Differential Geometry, Continuum Mechanics, edit with Michael Griffith, Robin Knox, published a few years ago. If you're interested, you could find more examples here. And I hope I convinced you that nonlinear PDEs of mixed elliptic hyperbolic type or even no type very naturally arising many fundamental problems. The solution to those fundamental problems in either area greatly require a deeper understanding of nonlinear PDE of mixed elliptic and hyperbolic type and further development of new mathematics. So I think I stop here. I just call your attention and thank you very much.